Okay, so let me get started. I welcome the viewers to this problem solving and live interaction session for the subject experimental stress analysis offered by Professor K. Ramesh on the SWAYAM portal. So, my name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering at IIT Madras. I'm working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan. So, let us get started with looking at the contents of week 10 today. So, let me move on to the first question. So, the first question says, to comfortably use the strain gauge without any modifications to measure both elastic and plastic strains, the value of strain sensitivity of the conductor wire SA should be closer to what? The options give us 1, 2, 3, and the options give us 1, 2, 3, and 4. So let us take a look at this. So basically we are talking about a conductor wire here. So for a conducting wire, we know that resistance is given by rho L by A, where R is the resistance, rho is the resistivity, L is the length of the wire, and A is the area of cross section. So having said this, now if I were to, our motive in strain gauge instrumentation is to be able to relate the change in the resistance to the change in the length, basically strain. Change in length divided by the original length gives us strain. So we want to relate it to the change in the resistance of the wire by suitable calibrations. So from here, if I were to, let us say, take log on both sides, this gives me ln rho plus ln L minus ln A by our principles of logarithms, properties of logarithms, basically. So let me differentiate this. Let me take the derivative, total derivative. So this gives me change in resistance by the resistance is equal to change in resistivity by resistivity plus change in length by length minus change in area by area, the original area. So with this, let us proceed. Now what I can do is I can basically relate the area first. Now let us say for a circular wire, let's reduce this a little bit. For a circular wire, let the area be given as pi d squared by 4, where d is the diameter of the wire. So from here, this is just a small aside. From here it follows that dA is 2 pi d by 4 into the change in the diameter. So therefore, dA by A is nothing but pi d by 2 into change in the diameter whole divided by the actual area, which is pi d squared by 4. So the 4 would appear here. So this follows that dA by A is nothing but, I'll just cancel out whatever cancels out, pi cancels out, one of the d's cancel out, and this becomes 2. This becomes 2. So this gives us 2 change in the diameter by the diameter. So we have been able to relate this like that. Change in the area to the change in the diameter, or rather, now for a circular cross section, this is basically the lateral strain. This quantity is basically the lateral strain. Now we know that the lateral strain by the longitudinal strain is defined as Poisson's ratio. We know this from our basic understanding of strength of materials. So therefore, this follows, so therefore dA by A can be written as 2D delta D by D, which is equal to minus 2 mu delta, or rather dl by L. What have I done here? I have simply put the longitudinal strain, multiplied it by the Poisson's ratio and added the negative in order to honor this relation. And I have substituted it. That is all that has been done here. So let me go back and substitute this here. So what do I get from the equation now? So this gives me dr by r. It's nothing but d rho by rho plus dl by l minus of minus 2 mu dl by l. So this gives me dr by r is dl by l. I can represent that as the axial strain. So this is nothing but the axial strain into 1 plus 2 mu plus d rho by rho. So this is equation number 1 we get here. Let us call this equation number 1. Now let me work upon this equation by simplifying things a little bit. Now from equation 1, we have this. Now we can define, let us define the sensitivity, or rather let me write it here. Let us define the sensitivity of a conducting wire as change as S capital suffix A. When we go for small suffix A, that denotes the sensitivity of a strain gauge. Presently, we are talking about a conductor, so this is capital A, is given by the change in resistance to the change in the length, so to speak. So, substituting this into 1, if I were to divide, so this follows that dr by r divided by dl by l gives me d rho by rho divided by dl by l plus 1 plus 2 mu, or rather let me write this again, saying that this is the sensitivity of a wire. Gives me 1 plus 2 mu plus d rho by rho by dl by l. So this is the strain sensitivity of a conducting wire. Now what does these quantities imply? The strain sensitivity of a wire, this shows that the strain sensitivity of a wire depends on the Poisson's ratio of the wire, the change in the resistivity, and the strain, change in the length. Now, what happens with this knowledge? if we were to see what happens at a high plastic strain, or rather, what happens at high strains. So at high strains, the conductor or the wire, the metal, becomes plastic, enters the plastic zone. Therefore, Poisson's ratio approaches zero point 0.5. At this time, Poisson's ratio approaches zero point 0.5. There is no change in the resistivity. So therefore, SA approaches 1 plus 2 into zero point 0.5, which means SA approaches the strain sensitivity of the conductor approaches 2. When at high strains, the strain sensitivity of the conductor approaches 2. So from this question, it follows that to comfortably use the strain gauge without any modifications to measure both elastic and plastic strains. If we did not accommodate this, then we would have to make suitable corrections. But for a wire which has a strain sensitivity close to 2, for a conducting wire which has a strain sensitivity close to 2, it can easily transition from elastic to plastic strains without any issues. So this has to be close to 2 in order for us to be able to use it comfortably without any modifications. So I suppose that is clear. This was just a bit aside to understand the thing clearly. Okay, so let us look at this question. Match the following with the applications. Now this comes under the topic of strain gauge selection. Now when we come to strain gauges, selection plays a major role, installation plays a major role, and what is the quantity? Not only in inside selection, the type of alloy plays a huge role on how we select. The resistance which we select plays a huge role. The connection that we give, the installation, how we conduct the experiment, how it is installed. So there are actually number of things that we need to take care when we go for strain gauge use. But nonetheless, it is a very versatile technique, as Professor also mentioned in the lecture. But a threadbare understanding of how the principles are derived and how they work would go a long way in using it effectively. This happens to be more of a statement of fact kind of question. So it might not have a logical, it might not have a derivation as such, but there are some things that experimentalists are required to familiarize themselves with over time so that we don't have to refer back the books wherever we go. Welcome. So the application states A, at room temperature applications, which of these is useful? For dynamic applications, which of these is useful? And for in situ measurements done over a long period of time, which of them are useful? Now, if we see what are the advantages of these, the Karma alloy has an excellent stability over time. So, therefore, naturally, it is suitable for making measurements where in situ measurements have to be made over long periods of time, for example, bridges and so on, just like health monitoring of bridges and so on. So there this is suitable. Now if we look at the advanced alloy, this has certain uh, interesting properties. This basically has a high sensitivity. It has a high sensitivity and a high fatigue strength, reasonably high. The isoelastic alloy also has reasonably high sensitivity and high fatigue strength. In fact, it is a bit more than what advanced has to offer. Now, given that these two are the applications, if we see the temperature sensitivity of advanced alloy, you can see that there is one graph that is provided, that how the apparent strain comes about with the temperature. Now, if we see, the graph would be something like this, where this band would nearly be the room temperature, around the room temperature. And if we were to see the same thing for our, if we were to see the same thing for the isoelastic alloy, it will be a very steep curve, nearly shooting up like that, which implies that slight change in the temperature during the application will actually bring about lot of apparent strain, which will disturb our readings. So for room temperature applications, we can see that this nearly has a stable response over that small window. So that is why advanced alloy is more suitable for our room temperature applications. While for dynamic applications which don't have much temperature variation, we need high sensitivity and high fatigue strength for applying it for dynamic applications. But since the constraint also says that one of the options has to be for room temperature, we generally go with advanced alloy for room temperature and isoelastic alloy for our uh, dynamic measurements. So there, when we come to strain gauges, there are certain things that we would need to remember or refer back to, but that is inevitable since there are more and more combinations and different products that are coming day by day. It is the requirement for experimentalists to keep up to date with these developments. Okay, so let us look at this question. It says, what is the percentage of error involved in the strain gauge measurement if the strain gauge is pasted on a 0.8 mm thick cantilever beam? So we are talking about a cantilever beam which itself is zero point 0.8 mm thick. It is a little bit less than an mm. So it is almost like a ruler, so to speak, a ruler or a thinner specimen than that. But for the sake of our understanding, let me draw it like that. Let this be 0.8 mm. And it is said that it is a cantilever beam. So let me fix it like that. Let this be subjected to some load, which has not been given actually. So let me just take some load for the time being. Since we are talking about beam, I take it that the predominant response would be bending. So I will confine myself to that alone. So they say, what is the percentage of error involved in the strain measurement if the strain gauge is pasted on a 0.8 mm thick cantilever beam whose grid plane is at a height of 0.06 mm above the surface of the beam. So what are we saying here? What is this grid that we are talking about? Basically, our strain gauge is made like that. It is made with these grids where this end is bulbous and will be connected like that. And this will go on to connect to the solder tab. So these will connect to the solder cap and there will be a backing and encapsulation and so on. So this is the grid that we are saying. But how we are looking at is we are looking at it from the sides. So this will basically be pasted here at some point. I'm just choosing that point arbitrarily. Now it is said that the plane, because this also has some thickness, so it says that this is 0.06 mm. The grid is 0.06 mm. rather not let me write it like that. This is the grid is 0.06 mm above the surface. Now this is also essentially coating, a variant of coating only, as we saw. Coatings have a faithful transmission of surface strains onto the coating, and they respond in different ways. If it is brittle coating, it will crack. If it is a photoelastic coating, it will get stressed, and we will be able to see some fringes. If it is a metal foil, there is change in the resistance. Change in the resistance is what we measure, which can be attributed to the change in its length. So grid is zero above the surface. Okay. So they say what is the error involved? So let us say that this grid did not have any thickness and we are making a strain measurement on the surface of the beam. So for the sake of simplicity, let us assume that the cross section is like that. Over here, the cross section over here is like that. And when I take the cross section here at the strain gauge, at the location of the strain gauge, so it is at the location of the strain gauge, I additionally have the strain gauge also on the top. I'll color it like this so that it is clear. Okay, so now we know, we take it that the beam is under bending. So what is the stress? Let us say at that point, at this very section, what will be the stress? It will be some moment by the moment of inertia into y. Y being the distance away from the neutral axis. So for first case, that is strain at the surface, we know that stress would be m by I of the beam into, actually this would be IZ. I'll take this to be Z, this to be Y, the measure Y. And X is coming out of the plane of the paper, which is along the span of the beam. So this would be sigma, and I'm not accounting for the sign, which is taken care. I take it that is clear, that is not any issue. Y, but Y here would be the depth by 2. Y would be 0.8 by 2. I take it that the neutral axis at the center, and we are basically measuring at the surface of the beam. So this is nothing but its depth by 2. So this is the stress there, which implies that the strain would be m by E I z into 0.8 by 2. Okay, so this is for the first case. Now let us consider this case. This is for this case, it is this. Now for the combined case, for the case where strain gauge is installed at 0.06 mm above the surface. So for this case, what would the stress be? Now we assume that there is no reinforcing effect of by the wire, by the strain gauge. So therefore, stress would be M by the same Iz into Y. However, Y would be D by 2 plus the distance of the grid. So therefore, sigma would be M by Iz into zero point 0.8 by 2 is half the depth plus 0.06 is what we are saying it is away. So this will be sigma in the second case. Let me call this sigma combined, and this is uh, just sigma axial. This will be EA. So therefore, the strain, the combined, the strain in the case where this combined setup is taken, it will be M by Iz into 0.8 by 2 plus 0.06. So therefore, error in strain measurement is nothing but epsilon C minus epsilon A by the actual epsilon A into 100. We're taking it as a percentage. So this will be, so what does this come out to be? Point. So M by Iz cancels out. So I need not even write it. So it will just be 0.406 minus 0.400 by 0.400 into 100. So what does this come out to be? 0.46. Yeah, sorry. This will be 0.46. Will be 0.46. Thank you for that. So it will be 0.46 minus zero point 0.4 divided by zero point 0.4. So this comes out to be 15%. Now we can clearly see that as the depth increases, the depth of the specimen increases, our error will also reduce. Now we made this assumption that it is not reinforcing. If we were to relax this assumption, then basically we'll have to take some contributory stiffness of the grid, and there will be a very minute shift in the neutral axis or the beam. But again, those approximations we are not going into, because in fact we have got this by applying the bending flexure formula, which itself is an approximation for a cantilever beam, because it doesn't have a neutral axis as such. So okay, so I take it this is clear. So we'll move on to the next question. So this is the error percentage. Four strain gauges are pasted on a shaft to measure the torque. For analyzing, answer the following questions. Okay, so there's only one question, which is what must be the angle theta in degrees. So we have a shaft which is applied with a torque. Now let me take this point. Let me take this point and let this axis be like that. Let this be Z, and we'll have this as R, and this will become theta, E theta axis, or Z theta, I'm saying. So if I were to draw this, now basically this is a case under pure shear. So I'll have a shear stress like that, and from our complementary shear stresses, I can easily draw the rest. So this happens to be my stress state at the point of interest. Now, what does this imply? That if I draw the Mohr circle for this, it is nothing but a circle with the center at the origin. So, for a pure shear stress state. So, the actual explain is over here or over here, depending on what we take to be x. So, this implies that when I rotate it by 45 degrees in the physical plane, I'll rotate it by 90 degrees in the Mohr circle. I will reach a case where I have only tension and compression. So, if I were to rotate this, or rather, let me not take it like that. If I rotate it by 45 degrees, I'll have this as compressive stress, and this will become tensile. And if this is of magnitude tau, we can see from the Mohr circle, this will also be tau. This will be minus tau. Minus I'm not writing because I've already indicated that with the sign. So in this case, we know that strain gauge can measure the strain along its gauge length. So we will have to orient this such that it captures this. So if we orient our strain gauge like that, it will capture this stress and this stress, this strain, which we can later convert it to stress and back calculate how what would have been the measure of tau, which we can relate to the torque by our simple uh, torque equation. So we will have to orient this at 45 degrees so that this measures. So even in the case, this is also an experiment offered here in our experimental stress analysis course, that is the lab course, where we basically we apply a torque onto a shaft, and then we have a rosette, a strain rosette that is pasted onto onto some point on the surface of the shaft. We make the readings and then we try to back calculate what would have been the torque applied or whether the torsion formula holds, and if it doesn't, why, what would have been the reasons for the discrepancies and so on. So I hope that is clear. Okay, so let us look at this question. How should the strain gauges be connected in a Wheatstone bridge to maximize the output signal? Is what is asked. So now if we see here, basically this goes by one convention. For a strain gauge, for a Wheatstone bridge, basically we go by one convention where we get the output, how shall I put this? For an initially balanced bridge, we'll get the change in output voltage given as the change in the voltage given as R1 R2 by R1 plus R2 squared into change in the first resistance. So how this is derived is basically we balance out the Wheatstone bridge. We write the equation relating all the resistance to the Wheatstone to the output voltage given one input voltage given one stimulus. What will be the change? we write the actual voltage, the output voltage in the form of resistance and the total voltage that was provided, and we take a total derivative. So that is how we get this equation. While getting this, 1 and 2 are in the adjacent terms, 1 and 3 are in the opposite terms. Now this follows that if we, the derivation for this is pretty much given in the lecture, so I'm not deriving it again. So what this means is the output voltage is given by, we generally take one factor, let us say R2 by R1. We'll name it some letter. I think it is M, that is what is named in the lecture. So if we work this quantity out in terms of M, it will come out to be 1 by 1 plus M squared or something. And then we'll just sum this up. So we'll take the same resistance and we have our change in resistance by the R. So this is the generic expression that we have here. Sorry. This is the generic expression. Generic expression for the output voltage. Now, if this were to be maximized, on maximizing the output voltage with respect to the ratio R2 by R1, which is M, uh, basically what we are doing is the partial derivative of the output voltage with respect to M and set it to 0 in order to find the extrema, the stationary point. So what this gives us is a function which has its peak at M equal to 1, at M equaling 1. So this implies that for maximum output, we need to have M equal to 1, which is R2 by R1 equaling 1, which implies R2 equal to R1. Now, for initial balance of a bridge, for an initially balanced bridge, we have R1, R3 equal to R2, R4. So therefore, this also follows that R3 equal to R4 equal to R2 equal to R1. So what we want is, we want all the resistors to have the same resistance in order to maximize the output of our Wheatstone bridge. So if we were to measure the same strain, for as explained in one of the examples in the class, where we have a cantilever beam and then we paste the strain gauges at the top and at the bottom, what we need to ensure is that, like the strains which are similar in nature, they add up, so they have to be appropriately connected, and the strains that are of equal magnitude and opposite in nature, they are appropriately collected so that they appear in the second and fourth position, so that the negative, the strain gets positive, becomes positive, and it adds up to the overall output of the system. So while we derive this, the arrangement that we go for is like that, where 1 and 2 are in the adjacent terms, 1, 2, 3, and 4. And we tap the output out of this. So here, let me delete this. So we'll give the input here. This is the input voltage, and we basically have the output like that. This is the output, which we are trying to maximize. So based on this, when we take the total derivative, we get this expression. So what this implies is that like strains need to be in the opposite arms, and unlike strains need to be in the adjacent arms, so that your output maximizes. And since we are looking at a full bridge circuit here, we are not looking at just one single strain gauge. So let us see the first option. We see that 1 and 2 are in the opposite arms. So here this would basically, even if 1 and 2 are pasted other these things, it will basically reduce the output. So A does not maximize the output. B definitely maximizes the output. C, if we see, we have a resistance here and then we have a resistance here, and then we have collected 1 and 2 in parallel. So basically this adds up to one cumulative resistance. Similarly, 3 and 4 adds up to one cumulative resistance. Now, let us say that we initially take a 350 ohm or 120 ohm resistor. We balance it out by keeping everything at 120, and then we connect it this way. So basically 1 and 2 are connected in parallel. So the cumulative resistance of that arm is no longer 120 ohms, which happens to be the resistance that we chose here. Hence, this will not be giving a amplified output. If we go to option D, it is nothing but C in another form, where we have switched 2 and 4. And this switching, we very well know that doesn't make any difference to the output. So difference to the output, that is anything different than B. So B and D give us the maximized output. And what will be the maximum bridge factor that is obtainable? We will get 4 times the output if the strains are similar and opposite in equivalent nature. That is the maximum we can get out of this. Now we seldom go for such arrangements. Generally, a quarter wave or a quarter bridge or a half bridge connection is what we generally do in our experiments. So for the quarter bridge, this has one issue of temperature effects. So that is why we would generally not go for two taps, but we will go for three taps, which is something called temperature compensation, which we will look in the next session as to how that affects and how we can get over temperature compensation by suitably tweaking our Wheatstone bridge arrangement by having a tap that has three wires instead of two, just for a quarter bridge arrangement. So I hope this is clear. Okay, so I take it is clear. Should there be any questions, you please feel free to ask. In the meantime, let us look at this question. The strain field in a component of interest is in the range minus 5 mm to 5 mm, where x varies between these, is as follows. 5, okay. So what they have done is, it is some problem that we have, where we have some origin. This is x, this is y, and z, and so on. So we have a band of minus 5 to 5. Yeah, so this sounds about right. So let this be minus 5 and 5, or rather, I took a poor example, I think. Let me take a simpler example. Let me take a beam. is simpler to elucidate the point. Let this be x-axis. Now what we say is let this be x equal to minus 5 and let this be that be x equal to 5 and let this be x equal to minus 5. So, so within this range, this is x equal to minus 5, this is x equal to 5. We have the strain in the x direction. It is not given as epsilon x. Okay, I'll take it as epsilon x, which is given as a function of x alone, 5x cubed plus 3x squared plus 4. So it has some cubic variation here, is what is given. And this they have found by some curve fitting or some mechanics of the problem, which they have been able to analyze it analytically. And for this, the domain of x is x belongs to minus 5 to 5. This is also given, which is where we are looking at it. Okay. Now, a general purpose strain gauge of gauge length 3 mm made of Constantan alloy having a wire diameter of 0.025 mm and specific resistance of 0.49 micro ohm meter is what is available for measurement. So some specifics are given for the strain gauge. So for the strain gauge, we have the gauge length equal to 3 mm. So if this is 10, this is 10 mm, our strain gauge will be this long at least. It is around 3 mm is what is given. Okay. And it is made up of a wire which has a diameter of 0.025 mm and it has a specific resistance of 0.49 micro ohm meter. So these things are given. This is fine. So this is what is available in the available for taking the measurement. If the strain gauge is pasted such that its center is at x equal to minus 2. So let me draw the line x equal to minus 2. X equal to minus 2 would be somewhat there. So this is x equal to minus 5. Let this be x equal to minus 2. So we have pasted the strain gauge. Let this be the strain gauge. This is of length 3 mm. So we have pasted this such that its center is at x equal to minus 2. So from here we can gauge that this end of the strain gauge is at minus 2 plus gauge length by 2 and this end is at minus 2 minus gauge length by 2 where L is the gauge length. Okay, now we have to answer the following questions with this setup. The average strain epsilon in microstrain measured by the strain gauge is what? Is what is asked. Now we know that when we have a strain gauge, a wire like that, basically it is measuring the strain. The change could be at any point, but we take the assumption that it is at the center. Let me draw it a little neatly. This I already have drawn somewhere. I'll just take it from there. Yeah. So in strain gauge analysis, The strain is basically measured at this point. Point where strain was intended to be measured. Now we go with the assumption that the average strain that is measured doesn't vary so much inside this gauge length of 3 mm, and we get reasonable values is the general assumption that we go with. Let us say how far the assumption holds in this case. How we can gauge that, because in this question particularly, we seem to have an expression for the actual variation of strain, which is stipulated by this function that is given. So now when we plug in the value of x, this also has one x. Sorry, I forgot about that. This has one 4x at the end. So this analytical expression we already have, from where we can actually evaluate the strain. And yeah, from here we can actually evaluate the strain. So let us see how that comes about. So the expression for strain is given by epsilon is 5x cubed 3x squared plus 4x is something we have. And this has some variation. So this will have some variation from here to here. This will have some variation along its gauge length, which will actually play a role in changing its resistance. But we would actually be seeing only one value that will be measured out of these ordering tabs. It is our assumption that we are trying to measure the strain here, whereas it is actually giving us the average strain of this length. And this length has a has a variation in the strain according to the question. So how do we go about doing this? So let us say that the strain variation was linear. In such a case, in between the two ends of the strain gauge, if this was linear, then basically our average strain at the center, if this is the center, then our average strain is not erroneous, because the average of these two happens to be the same. But in this case, we have a cubic variation. So how should we go about doing this is that we would have to calculate the average. Calculating the average strain. What we are trying to say is, if the strain variation is like that, if the strain variation is like that, then this area is what we are trying to find out an average. This is the total strain, and we want to idealize it as a rectangle. We want to idealize this as a rectangle, where this is the average strain and this is the length of the strain gauge. This is the gauge length. So we want to equate these two, is what we are trying to say basically. So how to go about doing that? How will we find the area? So the average strain epsilon average is given by the area under the curve. Which curve? It is the strain curve, which is given by this expression. So we are basically taking the area under this curve. Its domain still remains in x. So we just need to integrate this over the gauge length. Now we know that we want to integrate this over the gauge length divided by the gauge length, where L is the gauge length. So this implies that epsilon average will be integrated between, we have already seen here that the strain gauge is pasted at x equal to minus 2. So this spans, its gauge length spans between minus 2 minus 3 by 2 to minus 2 plus 3 by 2. So this will be minus 2 minus 3 by 2 to minus 2 plus 3 by 2. Here to integrate this expression and divide the entire thing by the gauge length, which is 3 by 2 minus 3 by 2. Actually, this is 3. So this is a simple thing to do. So the average would be, it will be 5x power 4 by 4 plus x cube plus 2x squared. And this we will take it over minus half, minus 2 minus 0.52 minus 3.5. So this we can just do, and the entire thing has to be divided by 3. So this will be integrating from minus 2 minus 3 by 2 to minus 2 plus 3 by 2, and we are integrating 5x cubed plus 3x squared plus 4x. So this comes to minus 168.75 divided by 3, which is minus 56.25 microstrain. So therefore, the average strain that is measured is minus 56.25 microstrain, meaning the strain gauge would actually read this as the reading. So the strain gauge will give this out as the reading. So this is minus 56.25 microstrain. What is the actual strain at this point? In many problems, this is actually not known, which is why we have to ensure that our strain gauge installation and selection and the appropriate gauge length is correct, because we don't have the luxury of this expression at our disposal. But for the sake of this question, we do have it. So what is the actual strain at this point? This point, the actual strain at this point is nothing but, we have the expression. The actual strain at this point is at x equal to minus 2, because that is where we have pasted the strain gauge with the assumption that the variation is not much and we are getting the average strain here. So let us substitute this. This will be epsilon p. So I'll just take this out of here to avoid clutter, and I'll put it here. So what is this? This will be 5 into minus 2 cubed plus 3 into minus 2 squared plus 4 into minus 2. So epsilon p comes out to be 5 into minus 8 is minus 40 plus 3 fours are 12 minus 8. So it is minus 48 plus 12. So this will be minus 30 minus 36. So epsilon p at that point of interest is actually coming out to be minus 36 microstrain. This is what our analytical expression gives us. Whereas what is the strain gauge measuring? Here we see that the strain gauge is actually measuring minus 56 instead of minus 32. Why is this? Because over the length of the strain gauge there is a sharp variation. So there is some error that is involved here. So epsilon t is actually minus 36 microstrain that is coming. So the that is what is asked. Error made in the measurement of as a percentage of epsilon t. So the error as a percentage is minus 56.25 minus of minus 36 by minus 36 into 100. So how much does this come out to be? Minus 56.25 minus 36. So this comes out to be, oh, 6.25 minus 36 divided by 30. Acha, this also happens to be 56.25. Okay, so the error comes out to be 56.25%. You can work it out. So we are almost halfway away. That is the actual error. We are overestimating it by 50%. Is what we are trying to say here. So what is the remedy for this? One way is that since there is a sharp variation, we can cut down on our gauge length so that we capture more or less a straight line, which is the basic principle of how calculus goes. The closer we make our interval, the more we can reliably estimate the function to be a straight line. And when it is a straight line, our average strain is at the center. So that doesn't make any difference, is what we are going with. So what this implies is at this point, if the strain variation is very high, if the strain variation is very high, then the average strain that we are trying to capture may be off by the peak strain by a significant amount. As we see here, it is almost 50% off. The question naturally does not say what is the application, whether it is just a first level analysis, because for a first level analysis, even a factor of this is acceptable in certain cases. So it depends on the application, but that is not the focus here. The focus here is to see how to mitigate this issue. If we need to refine our results, how to go about doing that. So the next question asks that if the tested strain gauge has 12 loops in its grid, calculate the base resistance of the strain gauge in ohms is what is asked. So let us go about doing that. Okay, it's the same question here. It is just pasted twice. So this is question number 10. This is also question number 10 here. Okay. So we know that a for a wire, the resistance is given by rho L by A. Now for a strain gauge, it is a grid of wire, so we need to account for the entire length. So therefore, so the resistance would be the specific resistance. I'll just take this data here. I'll keep this data here. So for this, the resistance of a single wire is 0.49. 0.49 into 10 power minus 6 ohm meter into the length. Length is the gauge length of a single, I'm not talking about the entire grid, I'm just talking about one gauge, one piece in the gauge length, and this should be divided by the area. So the area is 0.0025 mm to meter squared pi by 4. So this is for a single, that is, if we have the grid like this is just for this component. We don't consider the end tags because those are made thick specifically bulbous so that its contribution to the resistance is uh, low. In such a case, we just need to multiply it by the number of loops that are there. There are 12 loops. So we will get the base resistance that is required. So this will be 0.0025 into 10 power minus 3 by 4 into 0.49 into 6 into 3 into 10 power minus 3. 3 mm 0.0025 10 power minus 3. So this comes out to be 299, which is close to 300 ohms. So this question framed in such a way that you would require it to be 300 ohms, but I encourage you to check the calculations nonetheless. 0.0, okay, 0.025 I have taken 0. Okay, yeah, there is some problem here. What I have done is I took this to be 0.0025. This is 0.025. So let me recalculate it. 0.025 square pi by 4. So inverse into 0.49 into 12. So this comes out to be around 35.94. This is close to 36 ohms. Is what is needed. The base resistance for the strain gauge is around 36 ohms. Now the next question asks, if the gauge length was 2 mm as opposed to 3 mm, if the gauge length was 2 mm, what would be the error made in the measurement as a percentage of the actual strains, what is asked. So what we are trying to say, if the variation was like that, if we have the same area captured like this, or if we have the area captured like this, or if we go on reducing this, we will see that, let me color this in a different color. Yeah. So what we are saying is the blue one is the actual variation. If the blue one is the actual variation, the wider I go, the lesser my estimate of the average strain would be. And the narrower I have it, that is the lesser my gauge length, I'll have more chances of actually capturing the peak strain that is appearing. But the lesser the gauge length, the more problematic it would be for installation. So there has to be a trade-off between what is the accuracy that we expect and how much effort it requires to paste. By and large, we don't generally have this curve. We will not be having this curve with us. It is in this problem that we have an analytical expression. This is just for us to gauge where the stress concentration zone is and then appropriately try to paste it. Okay, so this is what we are trying to do here. What we are saying now is if the gauge length were to be 2 mm instead, what would be the difference? So if the gauge length was 2 mm, then the extents of the strain gauge would be, this is still pasted at x equal to minus 2. So this will be minus 2 minus 1 2 by 2. This will be minus 2 minus 2 by 2, or rather L by 2, let me say. This will be minus 2 plus L by 2, which happens to be minus 2 minus 1. So this will be minus 3 x equal to minus 1. So we have to do the same drill. So let us go ahead and put that here. Let me take the entire thing actually. I'll put this here. So this will come out to be, so the average strain is integrating from x equal to minus 3 to minus 1 of this function 5x cubed plus 3x squared plus 4x dx divided by 2 mm, which is the gauge length now. So it is simple to calculate this. So let us go ahead and calculate this. Integrating from minus 3 to minus 1, 5x cubed plus 3x squared plus 4x. So this comes out to be minus 90 by 2, which is minus 45 microstrain. E average. And what did we see? Initially it was 56.25, while the actual value was minus 36. Now we have gotten little closer to the actual value. So we have been able to reduce the error. So therefore, by reducing the gauge length, a more a closer estimate of the peak strain or the actual strain is observed. And we can also quantify how close it is. So we can just take the error. So the error percentage would be, the actual strain we saw here was 36, minus 36 microstrain. We saw here is 36, minus 36 microstrain. So I'll just calculate the error based on that. So this will be minus 45 minus 36 by minus 36 microstrain. So this will be, this gives us a 25% error. So we can see that earlier it was 56.25, the percentage error. So it has drastically dropped to half that value just by reduction of 1 mm in the gauge length, which suggests that the area where we are trying to study this is actually a stress concentration zone and needs to be handled very carefully. Because in the actual problem, we will not be having such nice expressions at our disposal for us to find out what the actual error would be. For an unknown problem, we don't know how the strain variation is. So we need to be sensitized to that, which is the entire purpose of this question. I suppose it is clear. So anyway, so uh, suppose I've run out of questions. So I hope I've done some justice to explaining this. If there are any questions, I'm happy to take them now. And I apologize that I couldn't hold the session yesterday because of some unavoidable reasons, which is why we had to schedule it today. So going forward, we will have today's the week 10 discussion. So we'll have week 11 and week 12, and we'll also have one comprehensive session of about an hour or so, which will cover the entire week 1 to 12, where I can pick some sample problems and I'll solve them. And should you have any questions, you can also raise them there. In the meantime, if there are any questions based on today's session or anything, I'm happy to take them now. Yes, please go ahead, sir. Yes. Yeah. 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 That is the first question we actually saw here. Basically, I'll just quickly go through that. The thing, yeah. Yes. So when we go to high strains, yeah. When we go to high strain, yes, sir. Yeah. Okay. No, the question said that in the lecture, the professor said, basically, this is the question. To comfortably use the strain gauge without any modification to measure both elastic and plastic strains, the value of the strain sensitivity of the conductor should be closer to which of the value is what is asked. So if we were to derive this, you can also see this thing later and how it is derived. So basically, what happens in plastic strains when the strains are high, our Poisson's ratio reaches a value of zero point 0.5, which makes our sensitivity nearly equal to 2 because there is no change in the resistivity of the conductor. So if we do happen to have a conductor which follows this, this implies that this can be seamlessly switched between the plastic to elastic transition zone, and it can still give us the correct answer when we take the transfer sensitivity of when we take the sensitivity to be 2. So we don't need to go for any additional corrections is what we are trying to say here. Is it clear, sir? Yeah, the gauge factor is dependent on this, right? Mu. So if we have a gauge factor that accommodates this change, then we can seamlessly switch between these two. Yeah, yeah, yeah. Okay. Any other questions? Okay, okay. Mr. Kannan, you have any questions, sir? Okay. Oh, okay, okay. Anyway, no, you are not able to follow because of my delivery or just that you are okay, fine. Okay, okay, okay. Oh, okay, okay, very well. Thank you, thank you. So, sure, sure, more than welcome. Yes, sir. Please go ahead, Mr. Shivakumar. Yes, sir. No, the big expressions, those will be provided as a data sheet. From basic mechanics or some first principles derivation, that you can manage easily. Yeah, yeah, that one will be able to do. Because the idea is not to check the memory behind this expression. The idea is the application. Even tomorrow, when experimentalists go to the field, they won't be remembering this. They'll only be referring it here and there. Idea is to know where to refer. That's very well. And thanks a lot. You have been closely watching and pointing out the errors. I thank you immensely for that. So this correction to that formula somewhere in the derivation, I think it got missed out. I'll definitely post a correction to this. Thank you very much. Very well. Okay. Well, if there are any other questions, I'll take it now. Otherwise, we can perhaps call it a day, and I'll post the video soon along with the correction to tweak this thing. So thanks. Yeah, thank you. Thank you. Thank you very much. Yeah, yeah, good day. Thank you. Bye.